below, okay, consisting of the masses M1 and M2, the massless cable here, which is attached to mass 1 and M2, and the massless pulleys, which is here, the two pulleys here, is released at time t equal to t0. Okay, the motion of the cable over the pulleys here occurs without frictions. That it means there is no frictions between the cable and the pulleys here. The coefficient of sliding friction between the mass M2 and the sloped plane during movement is mu. That it means here, let's say there is friction, okay, between here, the sloped plane and the mass M2. Then the motion occurs under the influence of gravity here, let's say given by G. Okay, what is given M1, M2, okay, the gravitational acceleration, friction, coefficient, the angle alpha here, and we say that M1, the mass M1 is greater than the half of the mass M2 sine alpha. Now, the question is, using both Newton and D'Alembert's laws, determine first the acceleration of the mass M2 here, the cable force, that it means the force in the cable here, when the mass M2 is held fast and when the system moves freely. Okay, these are, let's say, the questions. Yeah. Now, coming to the solution of this problem here, the first things I will go. Okay, then we have here then the exercise. And the exercise I made some tests, has worked perfectly, and now it's not working.
Doctor, you are muted.
Okay. Yeah, thank you. Yes, we said that here we have the two masses. Now we look to the forces which are applied on this two masses here, or two particles, M1 and M2. In our case, that's what we have. We have the external forces, which are the weight, G capital letter M1, G1, and here G2, capital letter 2. This is what we noted. I noted, yeah. This is the weight, G2, G capital letter 2, and G capital letter 1. Now what we have? We have the contact here between the sloped plane or the ground, let's say, okay, mass 2 with mass 2. Then there is the contact force here, which is N. As there is friction, okay, then will be included here the friction force R, which is equal only to mu, which is friction coefficient, multiplied by this normal force. Okay, when there is no friction, in this case, R is equal to 0. Okay, now for the first questions, what we have to look for first is to determine x dot dot 2. Okay, this is what it's asked for. That is means we have to look for the acceleration. In this case, what we have to do, we know that the sum of the forces, if we use now the Newton law, what we have here, let's say I make A, okay, I will make zoom, it's better. Here will be A, I write Newton here law, okay. Then in this case, what we have, we know that the equation is only the sum of the forces Fi, it's m multiplied by the acceleration here, let's say mi ei. Okay, then it means we have the sum of the forces, the external forces must be equal to the mass multiplied by the acceleration. Okay, now select it again. Okay, I close it again. Yeah, and I will return back. Okay, we said that the sum of the forces Fi is equal to mass Mi divided by multiplied by the acceleration Ei. Okay, this is the general formula. And if we look now what we have as forces, yeah, as we said, that is, we have the normal forces, which is the contact between the mass and the ground. We have the friction force, yeah. We have the weight G2, and we have the weight G1. For the method of the Newton, yeah, for the method of Newton, we have to make what we call the cutting. That it means we cut the system to know the internal forces. In this case, what we have, we look now. We take the cable, yeah, which is attached to the mass M1. What we have here, when we cut, that it means we look the equilibrium. The equilibrium, it's here with this force will be the force here, M1 multiplied by G. This is, I call it S1. Okay, this is also in equilibrium with the with the pulley, yeah, where you have here also when you cut, you have also the same forces here, M1 multiplied by G. This is S1. Okay, this is it's only G1, the weight, yeah. And here you have also the same. It must be in equilibrium as the force on the cable, yeah, is transmitted everywhere, yeah, on this cable. Then in this case, we have also here M1G, yeah, the same. This force is in equilibrium with this force as we cut the cable here, okay, there will be also M1 multiplied by G. The same, the force here, the cable force is transmitted also, yeah. Then we have here M1 also multiplied by G. Okay, then what we have to do, we assume that the motion in this case, it's in this direction. Then it means we have here for the mass 2, we take the direction x2 as there is only motion in this direction here, okay? And here we can take also x1, yeah? Then it means we will have here x2, the position x2, velocity x dot 2, and the acceleration x dot 2, what we are looking, yeah, which we are looking for. Then in this case, if we look for the equilibrium um, equation, yeah, what we have here, we look that M2G, yeah, can be decomposed into two parts, one in the direction of x2, okay, and one in the direction of y2. If we look only now to the static, okay, to be in equilibrium to decide in which direction is the motion, if we make in static, here I insist, yeah, we have, this is what you have done in mechanics 1. I repeat it always. I, Fi must be equal to 0. Okay, this is in static. Then it means what we have, if we look now the sum of the forces in x2 direction, okay, this will be equal to 0. In this case, we will have to avoid such problem because I'm losing Word document, which can help to represent the figure and so on. Then when we look here, what we have, if I return back now to the picture, okay, I will try to find now during my presentation, yeah, or during my, to give the solution to the, for this exercise, to find the solution that it will be more easy, yeah. Then we have fx2, then it means we can get that here, in this case, we have 2 m1 g, which is equal to m2 g sine alpha. Okay, then we see that here m1, I close it, I return back, yeah. Then we have, uh, we said that here, if we have two one multiplied by g equal to m2 or multiplied by g sine alpha. In this case, when we look that here m1, this is in equilibrium. In static case, here we have m1, it's the half, m2 sine alpha. Okay, this is what we get when we simplify here to get M1 as function of M2. Then we have this expression here. Then in this case, what we look, always the same system, but in any case, I will solve it soon. Then we get M1 here. This is the half of M2 sine alpha. In the exercise, it specified that M1 must be greater than the half of M2 sine alpha. Okay? Then it means here, according to this task, yeah, the motion is positive in x2 direction. Yeah, this is the choice. That it means when we move to, in this case here, when we move, we have M1, G is the direction of the motion. Okay, then it means the choice that we took for x2 will move, yeah, and along this direction here, yeah, that it means it's in the direction of M1, of the motion of M1. Okay, now I will try to solve this kind of the problem. Okay, I will try to use two, let's say, two software, the Microsoft Note and the Microsoft Word. Yeah, the Microsoft Word, I will use it to show the, let's say, the drawing or the picture of the system for each step, and the Microsoft uh, Note, I will use it to write. Yeah. Okay, we said that here in this direction here along x2 direction, there is the mass m1g. Yeah, this is here. If we look to the system here now, okay, alone, yeah, as we have done the cut, this is the method of Newton, which is the inverse of D'Alembert. Hello. Okay, this is when we cut here. This is the method of Newton. In any case, that we have to make um, a free diagram. Let's say this is when we make the cut here on the cable. We have M1G, M1G. That is means along this direction here we have two times M1G, and we have along this direction M2G sine alpha. Okay. When we look to this system here, only this part for the mass M2, the equilibrium is only that here we make in static the sum of the forces equal to zero. In static, that is means there is no motion. Then the sum of forces is equal to zero. We find that M1 is equal to the half of M2 multiplied by sine alpha. In the task of the exercise, it specified that M1 should be greater than the half of M2 sine alpha. That is means, in this case, the motion will be positive in this direction, x2. Okay. Now, if I take this part before to write the equations, that's what we have. In this case, as forces, we said we have N, the contact force, we have the friction force, R, which is here in our case, R, R, it's only the coefficient, friction coefficient multiplied by the normal or the contact force N here. Okay, this is the relationship between R and N. Now, if the motion is along this direction here, okay, then we have the cable force S here, which is also transmitted along the whole cable. That is means if we look now to the cable, we have the force in this cable is transmitted along, yeah, this cable here, which will be S. Okay. Now, return back now to the picture. We have R, which is mu multiplied by N. Then we have to look now to the equilibrium. In the local coordinate system for the mass M2, we have X2, which is the direction of the motion, and we have Y2. Okay, Y2, that is means there is no motion, yeah, in Y2 direction. For the mass M1, okay, the same system. We use the local coordinate system. There is X1, there is no motion in Y1 direction, okay? And we have the external force, which is the weight, M1 multiplied by G, and here M2 multiplied by G, okay, for the mass M2. Now, if we make uh, for the make the equilibrium equation according to Newton, okay, now I return back to here, Microsoft Note. And this is the problem that I had it also the last time. Okay. Now I close the Microsoft here, the OneNote, and I try to open it again. Yeah, and I hope this time the problem will be solved definitively. For this, I choose another way, but it seems that doesn't work with mirroring. That it means I am using another one tablet. Okay, it seems it's not working. No. Yeah, I cannot get the OneNote. Okay, document. I cannot see it. Now I have to shift to Microsoft Office, and I will open a new, okay, document. And this time I hope it will work without problem. Okay, then here we say the application. Hello. There is a noise like machine. Yeah. Then application of here Newton law. Then we have here along x2 direction. When we look to the sum of the forces along x2, this is equal to minus m2 g sine alpha minus r plus 2s equal to m2 x dot dot 2. Okay. This is the equation when I use this the equilibrium of the forces here. Yeah. When you look, the problem I have to return back. It's not easy, to be honest with you. When we look here now, what we have along this direction, x2, we have 2 times s, okay? We have here minus m2g sine alpha, and we have here minus r, okay? This is the equilibrium. Let's say we take them as external forces, okay? And after this, we have to do the same way in y direction. Okay? Let's say y2 direction. Then I return back. Then if we do now y two direction, what we have, you look to the picture, then it means that we have the sum of the forces along y2 direction here. It's equal to n minus n2 multiplied by g cosine alpha, and this is equal to m2 y dot dot 2. Okay, that is means if I return also again back, yeah, if I look to the picture now, along y direction we have n, okay, the component here in y direction is m2g cosine alpha, this component here, okay, and we have here also that we say if there is Newton law, that is means if we apply Newton law, in this case we have the mass 2 multiplied by the acceleration in this direction. But as I said, there is no motion along y direction. Okay? There is only the motion along x2 direction. Okay. Then what we have here, if I return back, then in this case, what we have y dot dot 2 is equal to 0. Okay, this is there is no motion along y direction, and we have additionally r. It's only mu multiplied by n. This is has been already defined, yeah, in the lecture. That there is also always this relationship between friction coefficient mu, yeah, and the normal force or the contact force, let's say. Then in this case, what we get here R, it's only here mu m2 g cosine alpha. Okay, then it means now if we take n, okay, here we have n, that is means here m2g cosine alpha, yeah, with minus n, and here equal to this term is equal to 0. Okay, then n will be only here. In this case, that we replace n by r, okay? Then we have here mu multiplied by m2 g cosine alpha, as n is only m2 g cosine alpha, okay? Then we have this relationship. Then we can put this terms here. In this equation, I call it equation 1. Okay, then we have in 1, then we get here the following equation, minus m2 g multiplied by sine alpha plus mu cosine alpha plus 2s equal to m2 x dot dot 2. Okay, this is what we correspond from the first equation. Yeah. Now we take here what we took. We take the application of Newton's law in x2 direction, in y2 direction, and now we look in in x1 direction. Yeah. Um, in in y1 there is no motion, yeah, also, but there is also no forces in y1 direction. Then what we have here in x1 direction, what we have the sum of the forces in x1 direction, let's say, equal to m1 x dot dot 1. Okay, then in this case we get here the sum of the external forces. Okay, there is only S and M1G. Okay, I return back. Here for this case, here for this mass M1, you have only S, yeah, and opposite to X1, and M1G, which is in the direction of X1. These are the external, let's say, forces. Okay, in Y1 direction, if we take here now Y1, yeah, in Y1, there is no force. Okay, if there is no force, that is means you have the sum of forces, yeah, which is equal to mass multiplied by the acceleration along y direction, yeah. The sum of forces, there is no forces is zero, yeah, and itself the acceleration also is equal to zero as there is no motion along y1 direction. Okay, now if we look to the expression of the equation now, what we have here, we will get that M1 multiplied by G minus S is equal to M1 X dot dot 1. Okay, this is what we get. Then we have here, let's say, two equations. This is I noted by 2. Okay, now we have to find now the relationship between the acceleration for the mass M1 and the acceleration for the mass m2. That it means for x dot dot 1 as well as x dot dot 2. Okay, this one here. This is we use what we call the kinematic relation. Yeah, how it happens, the motion, let's say. Okay, now if we look, so I will try to find now the way. One moment, yeah. It's fine. Okay, now if we look, we say that here kinematic relation what we have the displacement x1, it's only 2 times x2. Okay, now if I can explain it, yeah, turn back to the picture now. When you have here the displacement, for example, of this point here, okay, that it means if I draw, okay, the new position of the mass m1, it will be, for example, let's say it will be at this position here. Okay, there is here now the distance. This is will be the cover distance of the mass m1. Okay, will be x1. Okay, now when it moves here, the mass m1, this point here move to this point. Let's say gravity center, but it's make no sense, yeah, as it's mass m1, it's 1 point, yeah. Let's say we take the center of mass, let's say here, move to this position, then it's the cover distance is x1, okay. When it moves, that it means the mass 2 moves also, then it comes to this position, let's say. Okay, then this distance here yeah, this is now, okay, the distance, let's say x2. Now what we see, as it's not one cable, it's one cable, but due to the pulley here, this cable is divided into two parts. Okay, this is the cable part one, and the cable, yeah, turn around here to the part two. That it means the distance covered. If it's one cable, yeah, where the mass one is attached to the mass two only with one cable, for example, there is no pulley here, yeah, the distance x1 here will be equal to x2, okay? But in this case here, there will be the cover distance, the total cover distance here, it's x1, yeah, the cover distance here, let's say x1 will be 2 times of this distance here, x2. Okay, there is x2 here and x2 here. Then in this case, what we do, as we said, we make this kinematic relation, and there is always, yeah, this, when you find the relationship between two different acceleration, there should be one additional equations. Okay, additional equations. This additional equations will be always, yeah, the kinematic relation. Then we have this relation. Then we can write that here also, yeah, there is no additional condition. Then we can write that x1 dot dot will be equal also to 2 times x dot dot 2. Okay, then the distance here, the relationship, and here the acceleration, and it will be also the same for the velocity. x1 dot will be equal to 2 times x dot 2. Yeah, when we have this relationship, this is, we call it the equation 3. Okay, then we can find now that here we put 3 in equation 2, then we get here 2 times m1 g minus s equal 2 times m1 x dot 1, and this is will be equal to 4 times m1 x 2 dot dot. Yeah, this is the expression from here. Okay, and x dot dot 1 is only 2 times x dot dot 2, then which will give here 4 times m1 x dot dot 2. Then we get here, now this is the fourth equation. Then we get here from 1 and 4, we get the following relation. Then we get here G multiplied 2 times on M1 minus M2 sine alpha plus mu cosine alpha. This will be equal, I will write it here, for M1, I will write it here, yeah. This will be equal to 4 times M1 plus M2 multiplied by x dot dot 2. Okay, then what we have done, we have replaced only these terms, the relationship. We have x dot dot 2. Okay, we can define it by this relationship here. And additionally, we have here this relationship where you have x dot dot 2. Okay, then we combine this equation here with this equation, the fourth one. Okay, then we get here now the relationship. Then it means now if we know we um, look to the each term, G is given, M1 is given, M2 is given, okay, alpha is given, and mu, the friction coefficient, also is given, yeah, in the task. Then it means now we can get the expression of x dot dot 2, the acceleration of the mass 2 will be g multiplied by 2 times m1 minus m2 multiplied by sine alpha plus mu cosine alpha cosine alpha and divided by 4 m1 plus m2. Okay, this is the expression which is asked for. Okay, now if we look to the second questions, this is the first question. The second one questions, the cable force. That is means we have to determine this force S. Okay, now if we look for that we have here, then S, this is questions. What we have, it said that we take two cases. The first case is when the mass M2 is held fast. That is means the mass 2 doesn't moves, yeah, then we can say that in this case, the case A, we have x dot dot 2 is equal to 0. Okay, that is means is at rest. Okay, there is only static motion. Yeah. Then in this case, from 3, we can get also that x dot 1 dot 1 is also equal to 0. Okay, why? From the kinematic relation. Okay, when it's this terms is equal to 0, this terms automatically, yeah, is equal to 0. Then in this case, from here, the equation 2, we have S equal to M1 multiplied by G minus M1 X dot 1. This is the relation 2, and this is equal to M1 multiplied by G. Okay, we have in our case, as I said, here this terms is 0. Okay, then we have here, when we look now during the motion, this is now S, yeah, will be equal to 0. That is means it's only M1 multiplied by G. Then in this case, we have S, it's M1 multiplied by G. Yeah, and this is its logic. If you do static only, yeah, in static case, you will find that its S is only in equilibrium with the weight, yeah, G capital letter 1. Now, if we take the second case, here B, okay, now we have here x dot 2 is different from 0. In this case, what we have from 2, we have S, which is equal to M1 G minus M1 x dot 1. Okay, and this is will be here S equal to M1 G, and we are on place x dot 1 by the expression here as a relationship with x dot 2. Then we have M1 2 times x dot 2. And we have already the expression of x dot 2 is given by this equation here. We have to substitute. Then we get here, if you're on place, the value, you will get M1 G minus 2 times M1G, okay, multiplied by 2 times M1 minus M2 sine alpha plus mu cosine alpha divided by 4 M1 plus M2. And if we substitute here, you will get here, we arrange this equation as 1 will be M1 multiplied by G 1 minus, and here you have 4 minus 2 times M2 divided by M1 sine alpha plus mu cosine alpha. And here 4 plus M2 divided by M1. Okay, this is the expression of S. Okay, this is the expression of the uh, force in the cable. Okay, now if we look to the same equations here, but using D'Alembert, okay, relation. Now if we have here with D'Alembert, the same principle. The difference is only we say that in Newton law, we have to make the sum of the forces which equal to the mass multiplied by the acceleration. In D'Alembert, what we have to do is only to say the sum of the forces is equal to 0. But we have to introduce the inertia forces. The inertia forces are always against the direction of the motion. Okay? Means if we look now to the picture here, we see that is the same. What we have as external forces as for uh, the case of when we apply the Newton law. That is means we have M1G, okay? We have the cable force S, okay? The same cable force is transmitted along this um, uh, uh, let's say everywhere on the cable, the same force S. Okay, we have the friction force R, we have the contact force N, okay, and we have the weight of the mass M2, okay, and we have M2G, yeah. The motion is along X2 direction, yeah, and here we have X1 direction. Now, the differences is only, we say the sum of the all these forces, okay? For example, here for the mass M1, we take S, which is negative, minus, plus, with minus, plus M1G, yeah? This is the external forces, equal to the mass multiplied by the acceleration x dot dot 1, okay? Now for the D'Alembert, we introduce the inertia force, yeah? This is I call it, yeah, or I noted it by F1H. Okay, F1 corresponds to the mass one, yeah, H, let's say horizontal. Okay, that it means that here, yeah, if you remember, we say in the lecture we note it also by Ft. Okay, now what we have here, this force is only the mass multiplied by the acceleration. The acceleration of the considered point, particle, or body. Okay. Now, what we have, the direction of this force is opposite to the direction of the motion. Yeah. The same principle will be used here for the mass M2. We have the motion along this direction, positive direction. Now, F2H, yeah, which is the inertia force of the mass M2, will be opposite to the direction, yeah, of to the motion of M2. Okay, then we use the same principle. The differences, as I said, we said that the sum of the forces, yeah, xi is equal to zero. Yeah, this is important. Okay, Newton, we say it's mi xi, yeah, x dot dot I. This is what we do in Newton. Okay, now if I look to the equation, you will see we describe, yeah, the same equation as for Newton. What we have the sum of the forces of x1. Okay, if we look to the forces, we have minus m1 x dot dot 1 minus s and plus m1 g equal to 0. Okay, now this term here, it's only fh1. Okay, this is the inertia force, yeah, of the mass m1. The same principle for the mass 2. We have the sum of the forces x2 will be equal to minus m2 x dot dot 2 minus m2 g sine alpha minus r minus 2s equal to 0. Okay, Then we have here this expression here. It's only F to H. Okay, this is the inertia force, yeah, for the mass M2. Okay, if you look now to the equations, if you put this term here on the right hand side, this term here on the right hand side, okay, you will get the same expression as for the Newton law. Yeah, then to determine it, the equation that what we asked for, yeah, we have not repeated it. It's only to make the relationship or the kinematic relation between the acceleration of the mass 2, yeah, and the acceleration of the mass m1, okay? And we use the same step. This equation here, okay, it's only, I call it 2 prime, yeah, and this is here is the expression 1 prime. The important thing is this one, yeah, the two relation applying either Newton or D'Alembert. The second thing, yeah, which is always important, is to make, if you have two um, uh, bodies or three or yeah, more than one, in this case to find the relationship between the position also. In our case here, we need only the acceleration to find this kinematic relationship between the two acceleration. Okay, this is the third one. Why we cannot solve the problem otherwise? Yeah, because what is here when you see R, yeah, we have two equation. One, which is equivalent to 1 prime from D'Alembert. We have the equation 2, okay, here, which is sorry, this is 2, yeah. I make a small mistake. This is 2, okay. Then we have here um, this is 1. No, it's right. Sorry. This is not 2, it's only the change of 2. This is only a replacement of uh, R. Okay, this is the 2. Now, if we look here, you have S, which is unknown. Okay, acceleration x dot dot 1, it's also unknown. Okay, if you look to this equation here, we have S, which is unknown. Okay, and x dot dot 2 is unknown. That is, you see that you have here, let's say, one parameter, okay, or one variable, second variable, here the third one, okay, and you have only two equations, okay. When you are looking for to determine the cable force or to determine the acceleration, yeah, you need the third equation to solve the problem. The third equation will be always, yeah, in the majority of the cases, yeah, the relationship between the acceleration, which we will call it the kinematic relation. Okay, I think it's um, enough for today. Yeah, for now, let's say I will make